Um, Thank you, Chair. Can people hear me?
Yes, we hear you just fine.
Okay, well, really sorry not to be with you. I'm going to really talk about all the phenomena which can't be understood by present-day physics and need what I would describe as more physics rather than metaphysics. Of course, we know the laws of physics, which are established locally, apply everywhere we can observe with our telescopes, and also throughout cosmic history back to 1 second, when helium and deuterium formed. In fact, we can be confident of our knowledge of physics back to about a nanosecond. That's when each particle had about 50 GeV of energy, as much as can be achieved in the biggest CERN accelerator. And at that stage, the entire observable universe would have been squeezed down to the size of our solar system. Were there not this uniformity, of course, we make no progress at all in astrophysics. But fundamental questions like, where did the fluctuations come from? Why was the early universe made up of the actual mix we observe of protons, photons, and dark matter? These questions take us back to the even briefer instance within the first nanosecond, when the visible universe was hugely more compressed still. Indeed, if inflation theories are correct, down to microscopic size. Lab experiments offer no direct guide to the relevant physics at these extreme compressions. Though inflation is a consequence of specific, though still conjectural physics. Some assumptions give inflation, others don't. Here's another basic question. How much space is there altogether? How large is physical reality? We can, even in principle, only observe a finite volume, a finite number of galaxies. That's essentially because, like on the ocean, there's a horizon. And unless we take a very non-Copernican view that we're at the center, there will be galaxies that are already beyond our horizon. And in an accelerating universe, we will never, even in principle, observe them. So physical reality is certainly much bigger than the region we can see in principle. How much bigger? Well, there's no perceptible gradient across the universe we can see, looking from as far as we can in one direction and the other, which suggests that the universe contains about as 1,000,000 times more galaxies than the ones we can now see. But that's just a minimum. If it stretched far enough, then all combinatorial options could be repeated somewhere. Far beyond the horizon, we could all have avatars. Well, be that as it may, even conservative astronomers are confident that the volume of space-time we can ever observe, even in principle, is only a tiny fraction of the aftermath of our Big Bang. Our Big Bang. And then there's something else, of course, because scenarios like Ande Linde's eternal inflation suggest that the aftermath of our Big Bang could be just one island of space-time in a vast archipelago. It would be just one Big Bang among many. So a challenge for 21st century physics is to answer two questions. The first, are there many Big Bangs or just one? And second, if there are many, are they all governed by the same physics or not? Many string theorists argue that there could be a huge number of different vacuum states, different vacuum energy, different microphysics. And if that's so, other Big Bangs may, when they cool down, be governed by different laws. What we call laws of nature may, in this grander perspective, be just local bylaws governing our cosmic patch. And this offers the opportunity, as Thomas indicated, for anthropic selection. And it's really interesting for theorists to model counterfactual universes with different gravity, different microphysics, and so forth, to explore what range of parameters would allow complexity to observe, and which would lead to sterile or stillborn cosmoses. This is what is called anthropic selection. Are we in a typical member of the subset of these possible cosmoses predicted by the theory, which could allow complexity. Well, some don't like the concept of such a vast and varied cosmos because it would render the hope for neat explanations of the fundamental physical numbers as being entirely wrong, just as Kepler's numerological quest to relate planetary orbits to nested platonic solids proved to be vain and irrelevant. But our preferences are irrelevant to the way physical reality actually is. So I think we should be open-minded to the possibility of a fourth and grandest Copernican evolution. We've had the Copernican revolution itself, then the realization that there are zillions of planetary systems in our galaxy, then that there are zillions of galaxies in our observable universe, but we then realize that our entire observable domain is a tiny part of a vastly larger and possibly very diverse ensemble. To address this question, we would have to know the probability distribution and the correlation between them of these different universes. And that's a can of worms that we can't yet open, and it'll have to await big theoretical advances. I must re-emphasize that we don't know if there are other Big Bangs. But they're not just metaphysics. We might one day have reasons to believe that they exist. To be more specific, if we had a theory that described physics under the extreme conditions of the ultra-early Big Bang, and if that theory had been corroborated in other ways, by, for instance, deriving the unexplained parameters in the standard model of particle physics, then if that particular version of string theory predicted multiple Big Bangs, in other words, if it fulfilled the criteria for Linde's model, then we should take that prediction seriously. And there'd be no reason to assign those other universes, the aftermath of those other Big Bangs, a different epistemological status from the unobservable domains beyond our horizon in our own Big Bang, and indeed beyond the region inside black holes in our universe, where we think we know what's going on through Einstein's theory. So we would believe that the predictions of other Big Bangs exist if it was a consequence of applying to the early universe a battle-tested theory which had correctly predicted the values of some basic physical constants in our low-energy universe. And this is now an open question, but I think we should accept it as that, although we don't really know how to bet. In fact, about 15 years ago, I was on a panel at Stanford University where we were asked by the chairman, who was Bob Kirshner, how seriously would we take the multiverse concept. On a scale, he asked, would you bet your goldfish, your dog, or your life? On that scale, I said I was nearly at the dog level. And Andre Linde, also on the panel, said he'd spent 25 years promoting eternal inflation, so he would bet his life. Well, later, on being told this, Steven Weinberg said he'd happily bet Martin Rees's dog and Andre Linde's life. But the main point is that we should be open-minded about these theories. They're the consequence of uncertain physics, but if the uncertain physics has some parameters in it, we get eternal inflation, for others we don't. Well, how long will it be before we actually have a theory that allows us to address the very early stages of the Big Bang when inflation might have happened? It could be that some of the crucial physics of these unified theories could be just too difficult for human brains, just as quantum theory is too difficult for monkeys. It's conceivable, though, that machine intelligence could explore the 10-dimensional geometrical intricacies of some string theories. And then it could perhaps, having done that, spew out, for instance, the correct mass of the electron or other key parameters of the standard model. If that happened, we then have confidence in the theory we'd fed into the computer. and we would take its other predictions seriously. But we'd never have the aha insight moment, which is the greatest satisfaction for a theorist. But we would have reason to take the theory seriously if it had predicted things that we can test. Even worse, physical reality at its deepest level could be so profound that its elucidation and comprehension would have to await emergence of some post-human species. It may be that we will never be able to do this. There's no particular reason why our intelligence should be matched to the deepest aspects of reality. But let me close my last minutes with a plug for astronomy. It's the grandest of the environmental sciences. And thanks to improved instruments on the ground and in space, the subject is becoming broader. For instance, we know that most stars are orbited by retinues of planets, and there are billions of places in the Milky Way which could be abodes for life, but we don't know if they are. And, of course, physicists should always be modest and accept that biology is a far harder subject. The complexities in the understanding of the brain are beyond anything in physics. But astronomy, as well as being an environmental science, is also a fundamental science. Because to understand the very beginning of our expanding universe will require advances in physics, which may take us further from our intuitive concepts than quantum theory and relativity already do. Indeed, as I said, we must be open-minded that these concepts may be too deep for human brains to grasp. But they're still physics, even though they're speculative physics and maybe have to await post-humans. So let me end with a famous admonition from Hubble. He says, only when empirical resources are exhausted should we enter the dreamy realm of speculation. Thank you.